Yes.
Yes.
Okay, good. Again, Santiago's here. Santiago. Ryan Fila is here. Okay, again, good afternoon, everyone. I hope everyone is fine. So, last time we spoke about numbering system conversion. So we saw how we convert from decimal to binary. We mentioned decimal number has 10 symbols. From 0 to 9, 0, 1, 2, 3, up to 9. And this numbering system, which we use every day, like any calculations you do, you use numbers between 0 and 9, symbols between 0 and 9. Then we spoke about binary numbers, and this we only two symbols, 0 and 1. Okay. Thank you. Thank you, Nermi. Thank you. Okay. Then we spoke about octal number, and we mentioned for octal number we use 8 symbols from 0 to 7. Then we spoke about hexadecimal number, and in hexadecimal system, number system, we use 16 symbol from 0 to 15, but up to 9, we use letter A for 10, B for 11, and so on. And we saw how we convert from one system to another. Then we spoke about sign magnitude representation. So we mentioned we add bit 0 to represent a positive number and bit 1 to represent a negative number. Then we spoke about 1 the complement to represent negative numbers. So we mentioned it's simple, just invert both the positive number and then invert the bits. Today we'll continue. So we'll talk about the two's complementary representation, and this is the numbers we use in our computer to represent negative numbers, two's complement. So say we need to get the binary equivalent for 86, for example. So 86 as positive number is represented by 0, 1, 1, 0, 1, 0, 1, and the last bit here is 0 to represent the positive number here, right? So 86 is the sum of 64. We see these are the weights here, 1, 2, 4, 8, 16, 32, 64. As we mentioned, we double the numbers, 1, 2, 4, 8, and so on. And this came from, again, this came from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. But now we know that these are directly is 1, 2, 4, and double the numbers. So if you add 64 plus 16 plus 4 plus 2, you get 86. In two's complement, how we get the two's complement format for this number? We copy the bits. We copy the bits until we reach bit 1. The first bit 1 we reach, we copy bit 1 as it is, and then invert. So here we have 0, so we copy 0. We have 1, we copy bit 1, and this is the first bit 1 we meet now. Of course, we go from right to left. So we copy bit 1. Then we invert. So we have bit 1 here, so invert it to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, and the last bit here, which is 0, inverted to 1. To check. So this now, this binary representation here, in the two's complement format, represent minus 68. Represent the negative number of 68, minus 68. Minus 86, sorry, minus 86. We need to check. How we check if this binary bits correspond to minus 86? Again, put the weights: 1, 2, 4, 8, 16, 32, 64. And the last one is not 128, is minus 128. In two's complement representation, the last bit here is negative number. Then add. So minus 128 plus 32 plus 8, because under 8 we have 1 here. So plus 8 plus 2, we got minus 86, which is correct. The same like we did for 1's complement to check the number, except one thing. Who remember what we did for 1's complement to check the number? We did the same thing except one thing. One more thing. So what we did?
We add 1.
Oh, I added 1. Perfect. What's your code, sir?
7.
7. 10?
Yes.
Oh, okay. Thank you. For the people who just joined us today, unfortunately, yeah, missed the 2 classes. So your participation in the class is important, besides your attendance, of course. And when you contribute or participate with me, you get bonus credit. This bonus credit, we have 5%. If you look at, please read the syllabus carefully. The people who just came today, review the syllabus carefully, please. And you can see 5% for participation and attendance. So based on your participation here, I put mark. I put, as I mentioned, I add credits for anyone participate. And then I look at these participation, how much participate for each one. So you get maximum or good point for participation. And as I mentioned, at the end, if your final grade borderline the higher grade, based on participation here, I promise you will get the higher grade. But just to be borderline, not away from the higher grade. So as I mentioned, this, because I believe this participation is important for better understanding for what we discuss. So I encourage everyone to participate. Okay. Okay, so the only difference when we check the for one's complement, after we calculate this, we add +1 for convenience to get the corresponding or the correct negative number. I told you last time that some people ask questions about this. So I told you that we'll do example for this using the sign magnitude, one's complement and the two's complement. So this like a comprehensive example here. Express, and this is important example, please. So read it carefully. I mean, review carefully. And focus with me also. Express the decimal number minus 39 as an 8-bit as sign magnitude, one's complement, and the two's complement systems. So we need to get the equivalent binary for minus 39 in sign magnitude format, one's complement, and the two's complement. So we start first with positive 39. And we use 8 bits. Okay. So 39, if you put the weights here, 1, 2, we spoke about this at the beginning, how we convert from binary to decimal and from decimal to binary. So 1, 2, 4, 8, 16, double the numbers, 32, 64, 128. So these are corresponding to 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 39 is 32. So we put bit 1 here, plus 4, we put bit 1 here, plus 2, bit 1 here, plus 1. So if you add 32 plus 4 plus 2 plus 1, you get 39. And definitely, this positive number in sign magnitude, because we have 0 here. The most significant bit is 0 bit here. Now, to get this number, to get negative, this number, which minus 39, inside magnitude, what we do? Who remember what we do to get this inside magnitude, minus 39 inside magnitude?
Oh, we had 1 at the end. At the
exactly. We have
1.
We put bit 1 here. Okay, who mentioned this?
number 2.
Code 2?
Yes.
Okay, one else. I heard another one. Any other one? Okay.
I have a quick question now. Are we reading this right to left still? Or is this bit 1 in this case, or is it bit 8?
What is that? What is that?
In the sign. So are we reading right to left? Is it the last bit or is it the first bit?
This bit here.
Yes.
You see my cursor?
Yeah, I do. Is that would that be the
and I put here for negative. This bit 1 for negative.
Mhm.
Is this
It's the last bit.
0 for positive?
Okay.
Yeah. In sign magnitude representation. So we got the first part, sign magnitude representation. We just put bit 1 here. Now one's a complement. One's a complement. So we put 39 as positive. And then we just invert the bits. So bit 1 here inverted to 0, 1 inverted to 0, 1 to 0, 0 to 1, 0 to 1, 1 to 0, 0 to 1. The last is 0 to 1. And we need to check. We put this first, of course. Now we need to check this equivalent to minus 39. So we put the weights again. So 1, double 2, double 4, double 8, double the number, I mean. Then 16, 32, 64, and the last one, 128, but negative. Because we say this in one's complement. So the last weight here is not 128, it's minus 128. And add these numbers, which minus 28 plus 64 plus 16 plus 8 plus 1. So when we add this, when we add these numbers, we got minus 4. And as your friend mentioned, we add 1. So plus 1 to get the correct number. We add 1 for convenience. So when we add 1, we get minus 39, which is the correct number. Question here, please. When we add, I mentioned we add minus 128 plus 64 plus 16 plus 8 and so on. So why we didn't add 32 here? Why we didn't add 32? What do you think? We put minus 128 plus 64 z plus 16. Why we didn't put 32 here plus 32?
Oh, when it's a complement, the bit is flipped, so it's no longer 1, it's 0, so it's negligible, right?
What's your code, sir? What's your code number?
Oh, I think I'm 18.
Travis?
Yeah, that's me.
Okay, thank you. Is Travis is the only one who knows this?
No, I'm sorry. He was just the first to share.
Oh, sure. Okay, thank you. Garius, what is your code number? Garius? If I am right, I'm sorry if I don't say it correctly.
23.
23.
Yes. Thank you.
Gabriel?
Yes, sir.
Okay, please try to say, not go back and forth because this interrupts the class. We mentioned this before. Please. Okay. Yes, as he mentioned, you heard him, right? We didn't add 32 because you see, look at here, 32. Under 32 is bit 0. So actually what we do, 1 times 1 times minus 128 plus 1 times 64 plus 0 times 32, so which is 0. So I didn't put it here because when we multiply this, it is 0. Plus 1 times 16 plus 1 times 8 plus 0 times 4, so we didn't add 4. Plus 0 times 2, so we didn't add 2. Plus 0 times 1, it's 0. So we didn't add we didn't add 1 here because multiplied by 0. Okay. So after we inverted the numbers here, we just put the weights to add the numbers to check that we have really minus 39. Okay. Everyone see what I'm saying? If don't, please ask me what is not clear here.
I'm following.
Okay, everyone? Any question, please? So again, in what's the complement representation, we put the positive number here. And I just here for 8 bits, so we use 8 bits. So by default, you will see the last bits are zeros. Okay. Then using once a complementary representation, we just invert the numbers. We don't know this number yet. We know this number 39, but we don't know this number yet. So we invert the bits here. Then to make sure we have minus 39 here, so we put the weights as listed here. Then we add them up. So we got minus 40 plus 1. So we got minus 39. So we got minus 39. Now, 2's complementary representation to put 39, positive 39 as minus 39, how we convert it using 2's complementary representation. Again, we copy the bits until we reach bit 1. So the first bit 1 we reach, we copy this bit 1 as it is. Then we invert the rest. So we start with the first bit. We have already 1 here. So the first bit is 1, so we reach it to bit 1. So we copy the first bit 1 and then invert. So 1 to 0, 1 to 0, 0 to 1, 0 to 1, 1 to 0, 0 to 1, 0 to 1. And then we put the weights. We usually put the weights here, but because there is no space, so I put it here. It doesn't make difference, okay? So the weights 1, 2, 1 came from 2 to the power 0, which is 1. Any number to the power 0 is 1. Then 2 to the power 1, which is 2. Then 2 to the power 2, which is 4. So simply just double the numbers to get the weights. So 1, 2, 4, 8, 16, 32, 64, minus 128. The last number, because this is in 2's complementary representation. Not 128, minus 128. Add these numbers up, so we add minus 128 plus 64. No 32, because we have 0 here. So plus 16, plus 8. No 4, because multiplied by 0. No 2, because multiplied by 0. Plus 1. So we add these up, we got minus 39. So in 2's complement, we don't add 1 here, like in 1's complement. We add 1 to reach to the correct negative number just in 1's complement representation. So this is a good example here because we have the 3 representations of, or the 3 format to represent negative numbers. Sign magnitude, 1's complement, and the 2's complement. Any question, please?
Let's have a question. So when computers read binary numbers, how do they know that this binary number is for negative numbers?
The numbers are stored in 2's complementary format in the computer. The processor, I mean, is designed for this. The processor is programmed such that the store of the numbers in 2's complementary format. So if the number starts with 0, it will be positive. If the number starts with 1, like as I mentioned, here is the 2's complement. So for negative number is represented by these, by the corresponding binary here. If positive corresponding, I mean, represented by the corresponding binary number. So the numbers stored in the processor in 2's complement format or in registers or whatever.
Okay, thank you.
Okay, sure. So what is the advantage of using 2's complementary representation? What is the advantage? We have big advantage, actually. Addition of binary numbers is easier than subtraction. It's much easier than subtraction. So, if we need to subtract 2 binary numbers, so we just, like for example, perform the following subtraction of signed binary number. So we have this number minus this number. So we need to subtract. We can do regular subtraction, but as we mentioned, we have advantage of using the two's complement. How? This number minus this number, like this number plus this negative number. The same thing, right? And now we can represent this number as two's complement. So if this number, we put it in two's complement, so when we add 8 plus this number, we add like binary addition, but actually we subtract because the second number is negative already. So how we do that? First of all, we convert this to two's complement format. So 3, we need to subtract, right? So we take the second number here, 3, and we convert it to two's complement, or we put the format for two's complement. So again, we copy the bits until we reach to bit 1. So we copy this bit 1, then invert. So we already reached to bit 1 here. So we copy the first bit 1 as it is. Then we invert the numbers. So 1 to 0, 0 to 1, 0 to 1, and so on for the rest of the binary numbers. Let us check, is this equivalent to 2 minus 3 or not? So again, put the weights, 1, 2, 4, 8, 16, 32, 64, and the last one is minus 128. Add them up, minus 28 plus 64 plus 32 plus 16 plus 8 plus 4 plus 1. No 2 because multiplied by 0. We add this, we get minus 3. So now, this binary number here is actually negative number, representing negative 3. So now, when we add this plus this, it gives us the result of subtraction. So we put this one here, the first one, 0, 0, 1, 0, 0, 0, 0. And the two's complement format, this one, 1, 0, 1, 1, 1, 1, 1, 1. We add them. And remember, this represents negative 3. But we add, because already negative is embedded in this number, the negative sign. So 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0 with carry 1. So we put carry 1 here and leave it for a moment. Then 0 plus 1 is 1, plus 1, plus the carry 1 here. So it is 0 with carry 1. Then 0 plus 1 is 1, plus 1 is 0 with carry 1. Carry 1, we put it here. 0 plus 1 is 1, plus 1 is 0 with carry 1. 0 plus 1 is 1, plus 1 is 0 with carry 1. We ignore the last carry 1. Forget about it. Ignore it. So what this number represent? What this number represent is both the weights 1, 2, 4, and the rest are zeros, so you don't have to continue. So we have 4 plus 1, which is 5, which is the result of 8 minus 3, right? Right. So you see this advantage here or not? Okay. This also important example, please do practice again. And tell me, please, before you leave, tell me now if anything not clear here. Don't hesitate, just ask. Okay?
Professor?
Yes. Go
So
ahead.
for addition in two's complement format, do we always ignore the last carry 1?
Yeah, and when we do that, we ignore if we apply this approach here, so we ignore the carry 1, the last carry 1.
So when we try to do subtraction in the form of addition, we always ignore the last carry 1 to maintain the same amount of bits.
The bits, yeah.
Okay.
To keep the same pattern.
Same amount of bits. Okay, thank you.
Yeah, like here we have how many bits? 1, 2, 3, 4, 5, 6, 7, 8. So 8. So if we have another bit here, so this will be 9. So this is not this is not acceptable. We should maintain the same number of bits. The same bit pattern, okay? 8, like 8. Okay?
Does this rule also apply when we do pure addition in 2's complement format?
No. If regular addition, we did examples before. If you go back to, for examples we did,
Okay.
for regular addition, if we have carry 1 at the end, you put it.
Okay.
But here, ignore, because we use 2's complement format here. This is different story. We actually here subtract the numbers using 2's complement. Okay?
So when we do subtraction,
So we ignore the carry 1 here when we use this approach to subtract 2 numbers. So we use 2's complement here.
okay, so when we do subtraction in the form of addition in 2's complement format, where you can maintain
Whatever you got. So you just put, you don't ignore anything. In traditional either binary addition or subtraction, we don't ignore anything, but we ignore here as we mentioned to keep the same pattern.
Okay, thank you, sir.
Yes, as we mentioned, the computer is programmed for this. Okay, so don't worry about the computer. We need to understand what is going on here, how we use this, how we apply it. Okay, but what I mentioned, the negative numbers is stored in the computer in the 2's complement, or the numbers is stored in the 2's complement. Okay.
Professor,
Yes.
I was wondering, like if we're working with small numbers like this, is it, as long as we stay consistent with the number of bits, like you were saying before, would it be okay to turn it into 4 bits instead of 8, as long as we're consistent with the number?
Okay. Can you say your question again, please?
Well, I noticed that we would still be able to get -3 even if we only use 4 bits, just because we're working with such small numbers.
What
so
do
I
you
was
mean by
wondering,
small numbers? Do you mean?
like 8 and 3, like that sort of thing, as opposed to like much larger values.
No, I mean, to get the concept here, so we use these numbers. Okay. We need to just to get the concept, how we if we need to subtract, how we do that. Okay. Even if you have big number, you can use the same approach, just to double the numbers. Just say if we have like 1, 2, 3, 4, 5, 6, 7, 8. If we have more bits, so just double the numbers for the weights. Okay.
Okay, thank you, Professor.
What we did here is we understand this, or there's something not clear here. If you have question, it will be around these numbers. Of course, we don't want to make things complicated. Of course not. So don't worry about that. It will be similar numbers for what we do here. Okay. Any other questions? Okay. Decimal fraction and the binary fraction. How we represent this in binary? I mean, how we convert from decimal fraction to binary fraction, or from binary fraction to decimal fraction? So decimal fraction like this, like 3.5, for example, this decimal fraction. So we have a number after the decimal point. So like 12.625. And because decimal, so we use base 10 here. So how we convert this to binary fraction? Since we have decimal fraction, so the corresponding will be binary fraction. Again, put the number here, put the weights. So 1, 2, 4, 8. So, and the 12 is 8 plus 4. So this 12 as binary is 0, 0, 1, 1. So the weights on the left side here is 1, 2, 4, 8. And this again came from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. So what about the weights on the right of the decimal point? On the right of the decimal point, the weights 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and so on, 2 to the negative 4, 2 to the negative 5, and so on. So actually 2 to the negative 1 is 0.5. 2 to the negative 1, 2 to the power negative 1 is 1 over 2, which is 0.5. 2 to the power negative 2 is 1 over 4, which is 0.25. Then 2 to the power negative 3 is 1 divided 8. 2 to the power 3 is 8, which is 0.125. I just show you here how we got these 0.5, 0.25, 0.125. Now, the value here is 0.625. 6.625. How we got this number here? How we get this number here is 0.5 plus 0.125. If you add this plus this, you get 625. I mean 0.625. So this means we put bit 1 here because we need this number. We don't need 0.25, so we put bit 0. We need this number, so we put bit 1. Okay. So when we get this number, we multiply 1 times the 0.5 plus 0 times the 0.25, so it is 0. So 1 multiplied by 0.125, so we get 0.625. So the binary representation for this 12.625 is 0011.101 based on what we got here. So this is decimal fraction, and this is binary fraction. What is your question, Santiago? What's your question? Santiago, do you have question?
Oh no, I was wondering how would you write 12.626 instead of 12.625 into binary fractions?
Apply the same thing. Apply the same thing.
Okay.
You do more weights, and you may not need this. You need the other one. So just the same approach.
Oh, okay. Thank you.
Whatever you want to convert, just expand this, and I need this. No, I don't. So I put bit 1. I don't need this. I put bit 0, and so on until you get the number. Okay.
Professor, one question. How does the computer store the decimal point?
is based on, you know, you have central processing unit in the computer. So based on the way of storing, based on the way you programmed your CPU, so the numbers are stored. But binary numbers in general is stored in two's complement. So when we need to subtract the numbers, the processor just adds the numbers. And we'll talk about this later in details when we talk about computer structure and computer organization. We'll talk about this in details, okay?
Great, thank you.
You're welcome. Okay, now, if we have this binary number here, fraction, we see the point here. So how we convert it to decimal fraction? Okay, again, but 011 is corresponding to what? Decimal. But the weights 1 to 4. So 4 plus 2 is 6. 4 plus 2 is 6. We don't add 1 because multiplied by 0 here. Then point. Now put the weights here after this point here. So again, 0.5, 0.25, 0.125, 0.0625. And if we need more, so we can like 2 to the power -5. So just divide 1, divided 2 to the power 5. So you get the number. But we stopped here because you have only 4 bits here. So no need to put more weights. So to get the corresponding decimal point here, so we add 0.5. This multiplied by 0, so ignore it. Plus 0.125 because multiplied by 1. Plus 0.625 because multiplied by 1. If you add them up, you get 6875. 0.6875. So this binary fraction corresponding to this decimal fraction. Okay. Octal fraction to binary fraction. So this octal fraction, and as we see here, we have base 8. Okay, as I mentioned, we'll talk about this when we go to the computer part, okay? So just please be patient. Octal fraction, like we did before, we need to convert this to binary. So we just put the number 376 here, and we put the corresponding binary number. So 3 is 110. Again, you can use the weights. We have 3 bits here. For octal, we represent the number in 3 bits, 1, 2, 4. 3 bits, so the weights are 1, 2, 4. Or 2 to the power 0, 2 to the power 1, 2 to the power 2. So 3 is 1 plus 2, so 110. 7 is, we need 1 plus 2 plus 4 to get 7, so 111. 6 is 4 plus 2, so 011. So these are the corresponding binary for the octal part 673. Point, the same, 1, 2, 4. What's the corresponding binary? Just remember, we convert here from octal, not decimal, from octal. So 1 is 100, 2 is 010, 4 is 001. Up to here, please. Everyone knows how we get these corresponding binary numbers or no? up to here. Any question here? Any question here, please?
No question, I'm following.
Okay. Okay, good. So the corresponding binary fraction for this octal fraction is just to put these binary bits in sequence in the same order. Either if you start from the left here or if you start from the right here. Okay. So we got the corresponding binary fraction. Now we have binary fraction and we need to convert it to octal fraction. Again, look at the number after this point here. 110, 101, 011. This is the number. So again, divided two groups. Each group 3 bits. And the last time your friend mentioned why 3 bits. Why 3 bits, not 4?
Cause
He
just take,
mentioned,
oh, is that a question or no?
no, I mentioned your friend the last time mentioned why. So he mentioned because 8 equal 2 to the power 3. So we use 3 bits. Perhaps you answered this question before. I don't remember actually, but you got the credit anyway. So 3 bits to represent the number, any number in the octal format. So 3 is 110, 101 is 5, 010 is 2. One question here actually, when we divide these binary numbers, 2 groups, and each group is 3 bits. If the last number, we start from the right, we start from here. If the last number is just, say, 1 bit, just 1 bit, not 3 bits. So what we do? You see what I'm saying? We mentioned to get the corresponding octal number, we divide the binary numbers into groups. Each group 3 bits. We start from the right. So after 3, we take one group, the first 3. Then the next 3, we take another group. Then the last group, assume we have only 1 bit. Say bit 1, bit 1, but only 1 bit. There's no 3. So what do we do?
We add 2 zeros.
Exactly. Thank you. What's your code, sir?
Oh, 7.
7. Thank you. So we add zeros to complete the group. So say if we have 1 here and just 1 bit, and it should be 3, so we add zeros. We add 2 zeros. Zeros on the left doesn't make any difference. You didn't change the number. You just put it in suitable format for your calculation. Like, you know, when you change a form of equation to another form. So for example, if you multiply the left side by 2, so you multiply the right side by 2 also to keep the same equation. But this multiplication may put the equation in another format you needed for the solution. This is just a simple example. So when we add 2 zeros, we didn't change the number. The number is still the same, but we just complete the group numbers. Everyone see what I'm saying? Any question, please? Okay. So, okay, good. After the decimal point, after the point here, fraction point. So again, the same number here, divided into groups. Each group 3 bits. Start from the right towards the left. So 0, 1, 1 is 6, 0, 0, 1 is 4, 1, 1, 1 is 7. So now the corresponding octal fraction is 253.746. Any question so far? Any question? Okay. Okay, let us take like 10 minutes break, and then we'll continue the rest of the party. Okay, the rest of the class. So just please, 3:40 will be here. Okay.
Okay.
That
Okay.
So 10 minutes break, please. 10 minutes break. Okay, guys? Everyone is here?
I'm here.
Okay, good. Okay.
Welcome
Okay,
back.
so
Yes, we are here.
welcome back. Okay. Okay, so please let us continue. Now we'll talk about hexadecimal fraction and the binary fraction. To convert from hexadecimal fraction to binary, so we have like this example here, 306 point D for base 16 because we have hexadecimal here. And we need to know what is the corresponding binary fraction. Like we did from hexadecimal to binary. So we just take the first part here, 306, and under 6, what is the corresponding binary? The weights here is 1248. We use 4 bits for hexadecimal, not 3. And again, as your friend mentioned before, we have 4 bits here because 16 equal 2 to the power 4. So we use 4 bits. So 6 using the weight 1, 2, 4, 8. So 6 is 4 plus 2. So under 4 we put 1, under 2 we put 1, and under 1 we put 0, under 8 we put 0 because we don't need 8 plus 1. We just need 4 plus 2. So it is 0, 1, 1, 0. You see, I repeat many times, such that anyone missed a part can catch now, can catch up, okay? 0 is 0, 0, 0, 0. 3 is 3, we need 1 and 2. So we put 1, 1, then 0, 0. Okay. Now, point D, we mentioned D equivalent to 13 in hexadecimal. Hexadecimal after 9, we use A, B, C, D, E, F. A corresponding to number 10, B number 11, C for 12, D 13, E 14, F 15. So D is 13. 13 as binary is 1011. 8 plus 4 plus 1. So 1011. So just to put these binary numbers in order, so we got the corresponding binary fraction for this hexadecimal fraction. Okay. If we have this binary fraction and we need to convert it to hexadecimal, so again, divide this after this point, divide this binary to groups, each group 4 bits. And again, if the last group is not 4 bits, so complete 0, 0, or whatever missed, put it zeros on the left side, of course. So 1101 is corresponding to 11. 1 is 2 plus 1 is 3 plus 8 is 11, and 11 is corresponding to B. So this corresponding to B, 01106, 0011, which is 12, corresponding to C in hexadecimal. 0100 is 2. The same for after the binary, after this point, we divide it to groups, each group again 4 bits. So 0, 1, 0, 0, one group, 1, 1, 1, 1, another group, 0, 1, 0, 0 is 2, 1, 1, 1 is 15, which corresponding to letter F. So just to put the result here in sequence, so it's 2C6B point F2. Okay. Is this for fraction? Now we'll talk about any question, please. Any question here? Any question before we go ahead? Any question so far? Okay. Now we talk about coding. So binary coded decimal BCD code. This actually used for decimal numbers from 0 to 9. From 0 to 9, it can be encoded into BCD code. So just to put the corresponding binary. So 0 corresponds 0, 0, 0, 0. 1 is 1, 0, 0, 0. 2 is 0, 1, 0, 0. 3, 1, 1, and so on. And the symbol to write this, like if we need to write these numbers here. So the simple way is just to start 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, then double the numbers, like 0, double zeros, then followed by 1, so double ones, then 0, double 0, double 1, double 0, then double the number again. So 0, 0 is 0, 0, 0, 0, then 1, 1, 1, 1, 1, then 0, 0, and we stop at 9, of course. Then double again, so we have 4 zeros here, so we have 8 zeros here, and then ones. So just to get the whole BCD code for these decimal numbers from 0 to 9. So if we need to convert the number 1268 for base 10 into BCD code, if we need to encode this number into BCD code. So, like we did here, 8 corresponding to 0001. Of course, you can just put the weights also to get any one. So 8 is just the weights 1, 2, 4, 8. So you need 8. So 0001. 6 is 4 plus 2. So 0110. 2 is just 0100. 1 is just 1000. And then put all these binary numbers in sequence here in order. So you get the corresponding BCD. So to convert the number 1268 in BCD code, this is the corresponding code here. Again, in BCD format. If we have BCD format, the code is here. And we need to convert this to decimal number. So again, divide it to bits, or 2 groups, each group 4 bits, and with the corresponding decimal number. 1001 is 9, 11003, 0001 is 8, 01106. So just 6839. So this BCD code corresponding to decimal number 6839 is a code, is used. It's called the BCD code. Any question here, please? So far, any question? So here,
Professor,
yes, go ahead, please.
so BCD code is like a shortcut
It's
instead of
actually-
the like
it's
conversion
for-
shortcut.
to encode the 9 decimal numbers from 0 to 9. To encode from 0 to 9.
Right, so is it like a shortcut instead of having to divide everything by 2?
What do you mean
Yes.
by shortcut?
Like if we try to convert a decimal number to binary, we were taught to divide the
Oh,
decimal number
no.
by 2.
This is different.
Okay.
This is, if you convert this to binary, it will be different. This is the corresponding BCD code.
Okay, so this is a BCD format. Okay, I see what you mean.
Yeah, this is different format.
Okay.
For 1268 in binary is different. But in BCD code, this is what you got. Like
Okay.
here, okay?
So this is a specific binary format.
Yeah, it's called the BCD code.
Thank you, sir.
You welcome. Yeah, please, if you have question, just ask, please, okay? Okay, so, okay, let us go ahead. Another code is called gray code. Gray code is actually, it's important to code used in communication system for error detection. Is very important to code. Why? We'll see why. But first, how we convert from binary to gray code. So we need, for example, to convert 110 as a binary to gray code. So we put here 110, as you see here. Then start from the most significant bit here. We copy the bit here, either 0 or 1, so we put it as it is. Then we add binary addition. 0 plus 1 is 1, so we put 1 here. Then 1 plus 1, binary addition is what? 1 plus 1 equal to what?
0010 or just 2?
1 plus 1, what is the result in binary?
0, 1.
1 0.
0, 1 or 0 is carry 1, right? So we put 0 and ignore the carry. You put 0. This is the approach of converting to gray code. We ignore the carry. Any carry in any phase here, just ignore the carry. So 1 plus 1 is 0 with carry 1, forget about carry 1. So the result is 0, 1, 0. So 1, 1, 0 in gray code is 0, 1, 0. Everyone sees this?
Yeah.
Okay.
Yeah.
Now, if we have 1, 1, 1, for example, as binary, and we need to convert it to gray code, so we put 1, 1, 1. Then the first bit on the left, most significant bit, we copy the same bit, so is 1. Then 1 plus 1 is 0 with carry 1. Forget about carry 1. It's just a 0. We put just a 0. Then 1 plus 1 is 0 with carry 1. Forget about carry 1. So the result in gray code is 1, 0, 0. This is important to code. The gray code. Is clear or not?
It makes sense to me. You just add left and right, left from left
Yeah,
to right.
from left to right as we do here. And when we add binary addition, if we have carry, we ignore the carry 1. Okay? Now, why using a gray code is better for in communication system for error detection? Look at this table here. Look at this table. this is a binary representation here, like 0000 represent 0, 1000 1, 01002 in sequence. Represent the decimal numbers in sequence. So this is the sequence here. Okay. The corresponding gray code for each binary number here is this one. So 000 is 0000, like the same we used here. 1000 is 1000, the corresponding gray code. 0100 is drop the first bit as it is, so 0, then 0 plus 0 is 0, then 0 plus 1 is 1, 1 plus 0 is 1. So this is the corresponding gray code for 0100. The same approach we used, 1100, the corresponding gray code is 0100. 00110 is 0110. Any binary number here converted to the gray code, we use the same approach here we did. Okay. So we don't have issue with that. But look at the binary numbers here. These binary numbers, as we mentioned, these are in sequence, okay? Look at this number and this number, the next number for it. How many changes here you can see?
2.
2, perfect. What's your code, sir?
Number 10.
Number 10, that's good. So we have different people now. Okay. No, he said 2. Hold 1 second. My question is here. Let us go step by step. I know some people know this, but some others don't know. Okay. So we try to cover everyone. So we go step by step. So especially we look at here because this number comes directly after this number, but we have, this number directly after this number, but we have 2 changes here. In one transition, we have 2 changes. Look at here also, 1100. The next one, 0010. How many changes here?
3.
3. Perfect. Give me your code number. Code
3.
3. So 3 also. That's good. And what is the other one, please? I hear the
31.
31. Perfect. Thank you, Sam. Thank you. Okay. Okay. So we see sometimes from one transition, just one transition, we have more than one change. Now, look at the gray code. The first number here and then the next one. How many changes?
1.
1.
1.
How many changes here? Really?
Also 1.
How many changes here?
1.
1.
1.
And how many changes here?
2.
1.
1.
Why 2?
I don't know.
Sorry, 2.
Oh.
Yeah.
Just one, this one.
This one.
And so on. For each next gray code, we have only one change. Okay. For error detection, it's easier if you know that you have only one change or more than one change for the transition. Which is easier?
1 change.
One change, of course. If I know the next number we should have, each next number we have only one change. So is this, and we have error, this is much easier to detect the error rather than if you have, we know the next change will be like more, or the next transition will be more than one change, maybe 2, maybe 3, maybe more. So definitely, just this a hint for why we say gray code is used in, is important to code using communication system for error detection. Okay. Okay. Any questions so far, please? Any question? Byte, we know byte equal 8 bits. Word is group of bytes, maybe 2 or more. And the BC word size is most commonly 8 bytes or 64 bits. The ASCII code, ASCII stands for American Standard Code for Information Interchange. So it uses 7 bits. So 2 to the power 7 is 128 codes. It actually is extended for 8 bits. So so we have 2 to the power 8, which is more codes to cover more symbols and more, especially for other languages like a Chinese language or Japanese language. So they need more codes to represent all symbols. So it's mainly 7 bits, but it can be also 8 bits. So simply, if you have the ASCII code for 7 bits, to make it 8 bits, just add 0 at the left or at the most significant bit. The one on the left side, just add 0. So if we need to decode the ASCII code, this is ASCII code given here. And we talk about 7 bits here. So we divide this code to groups, starting from the right to the left, and each group 7 bits. So 1, 2, 3, 4, 5, 6, 7, one group, then next group, then next group, then next group. And we look at the ASCII code. I posted the ASCII code here for 7 bits. So what is the first part here, the first group? Is 1010, 011. So start 1010 here, on the left side here, based on this arrangement, okay? So if we have example like this, I will give you the same arrangement here. Okay, so don't worry about any change. So 1010, and then the other 3 bits left is 011. So we go 1010, then 011, which is here. The intersection of this and that is letter S, big S here. So the first part here corresponding to big S. Then 1010 again, 100. So 100 again here, and the other 3 bits is 100. So this and that meet at big T here. So this represents big T. Then 100, 1111. I mean 1001. That's the first 4 bits is 1001, 1001, and then 111. So 1001 is here. Then 111, which is O. Meet at O or intersect at O. So we have O here. Then 1010, 000. So 1010 and 000, which is B. B. So decode this ASCII code. So the corresponding is stop. So this ASCII code here means stop. Okay. Any question here, please? Okay.
So, Professor,
Yes, sir. Go ahead.
How does the code represent foreign language letters? Because there are like thousands of them.
Okay, if you go to if you Google ASCII code, either 7 bits or 8 bits, they will give you the whole representation for the symbols or symbols. So when you hit, for example, if I hit S on the keyboard, if you hit S, this is like analog, is analog. Must enter to the computer as digital. So this actually is converted to this binary number, 11000101. This is based on the code here. This is the ASCII code which we use it for computer. The keyboard, you have letters, the symbols, everything, and these are the codes which represent these symbols and the letters and the numbers, everything. If you hit T, big T, big is different than small t. Big T, this actually the input data to the computer is 0010101. I usually read from the right to the left. Okay.
Okay, got it. So it's for the keyboard.
Yeah,
different symbols.
this ASCII code used for the keyboard.
Okay, thank you.
You welcome. So because again, as I mentioned, the computer is digital processing. If you put analog directly, it's like a noise. It does not understand. We have to convert from analog to digital before it goes to the computer, like analog to digital converter. So when we hit S, D, S, F, or these all are analog. It's considered as analog signal or analog message. So when you hit S, it's converted to binary before it goes into the computer input. Okay.
Yeah, thank you.
You're welcome. A parity method for error detection. This is a method used for error detection in communication system. It's called the parity check or parity method. So what is this method? It's simply between the transmitter and the receiver, like there is agreement or protocol. So we say our protocol, just to make it clear, okay? Simplifying to make it clear. So we say the protocol between this transmitter and the receiver is odd parity or even parity. What this means? Odd parity means when I send a message, the whole number of bit ones, all bit ones, if we add the ones, is odd number. We know the difference between odd number and even number, right? Odd number, like what? Give me example for odd number.
3,
3, perfect. What's your code here?
7.
7?
Yes.
Thank you. Like 3, like 7, like 9, like 11. Any number cannot be divided by 2. Like 7 divided by 2 is 3.5. But 8 divided 2 is 4. So 8 is even number. 8, 10 divided 2 is 5. 4. So odd parity means the total number of ones in the message is odd number. Okay. Even parity, the total number of ones are even number. either like for simplicity 12, 24. So based on this method, the protocol between the transmitter and the receiver assume odd parity. So what happens? When we say type the message or send the message, there is algorithm in the system count the number of ones. So say the number of ones is even, like 12. But the protocol is odd. So in this case, there is order goes to the parity generator. There is a generator, generate bit 1 or 0, parity bit. So in this case, there is an order goes to the parity generator to generate bit 1. So when we add this bit 1 to the even number, it will be odd number. So the total number will be odd. And it transmits the signal or the message. As the receiver, the same algorithm. So count the number of ones. The total number of ones is odd. So this means the message is correct. Say when we put the message, the number of ones, the algorithm calculates the number of ones as odd number, and the agreement or protocol is odd. So there is an order goes to the parity generator to generate bit 0. So when we 0 added to the message, the number of ones is still the same odd. And send the message. As the receiver side, assume the message received has even number of ones, and the protocol is odd. So this means the message is not correct. There is an error. So the receiver asks the transmitter to retransmit the message because there is an error. So this for error detection, but not for error correction. There are other approaches, like it's called code word or forward error correction, can fix the message. If the message received in error, based on certain technique, the receiver can fix this error. But for parity, this is what happens. So in parity, either, as we mean in parity method, either we have odd parity or even parity. So let us look at this example here. Attach the proper odd parity bit to the following data. So the protocol here is odd parity. So this is a message here. So let us count the number of ones. How many ones here?
3.
3. So 3 is odd or even number?
Odd.
Odd, perfect. So what we add as parity? Parity
0.
bit 0. Where we put this 0? We put it
Beginning.
on the left side as the most significant bit here. Okay? Everyone sees this?
Yeah.
Okay, good. What's your code say?
30.
30. Okay, perfect. Thank you. Okay, good. We have more people to now participate, which is good. We have here for message B 1001 and so on. So how many ones here? Another one, please participate. How many ones here? How many?
2.
2. We have 2 ones in the message here. Is this even or odd? Same person, please. Even or odd?
Even.
Even. So what we need, the agreement or protocol is odd. So what we do? We add parity bit. The parity bit we add is 0 or 1?
1.
1. Where we put 1? Here.
At the
Okay.
end.
At the end, okay? What's your code, sir? What's your
10.
10. 10, perfect. I heard another one. So who's the other one?
31.
31. Okay, thank you. Okay. So you see, this simple, but unfortunately, if we have, like I had question before for my students, so they like put this 0 on the right side, or this one on the right side, for example, which is not good, of course. The parity bit added to the left side. Okay. Okay, great. So okay, so almost done. So we'll continue next time for new subject. Okay. Any question, please? Any question so far? Okay. Ryan Fila is here. Ryan Fila. Okay. Any question, please?
Professor, I have one question. So
Yeah, go ahead.
since the parity checker adds either a 0 or 1 to make sure the binary number adheres to the protocol, so in a
Mhm.
sense, why it's only useful for error detection, not error correction? Because in a sense, it adds number to the front, right?
No, error correction means error correction. Okay. Using this technique, oh, okay. Okay, we must add something here, but using this technique, what we did, the protocol is either odd or even. So if the protocol is odd and you received or the receiver received even parity, so this means the message is not correct. So we discovered the message is not correct. But this technique does not fix the error. We just say, oh, we have wrong message here because the number of ones must be odd if it is odd parity, or the number of ones must be even if it is even parity. So we just know that the signal or the message we received is not correct. But this technique does not fix the error. And there is also actually this is disadvantage, of course, definitely. But it is used. Another disadvantage here. Say, okay, say, let me just 1 second, please. Let me share with you this. You see this board? Oops, sorry. What is this? Okay, let me just, okay, hold on a second. Some issues. Okay. Okay, say we sent 0 1 1 0 0 1 0. So what is this? What is this odd or even?
Odd.
Odd. Perfect. So this is correct. Miss, if the protocol is odd, assume double errors happen. So say the message should be like this, but what we receive is this. So what is the number here? Is this still odd or even?
It is odd.
Still
Odd.
odd.
Still odd, but wrong message. Why? We have double errors here. So if we have double errors, so the message we receive, it looks like correct, but actually is wrong. It's not correct because double changes happened here, double errors. So this is another disadvantage for this approach. So the one disadvantage, as you mentioned, yeah, they just used for detection, not correction. Second, if we have double errors, so this gives false signal, which it seems correct, but actually it is not correct. If we have more time later, I will show you how we use another approach. It's called the forward error correction, based on Hamming code, how we correct the message itself if it is received wrong. How this approach fixes the message if it is received wrong. But if we have, because it's not included in here, but if we have more time, we'll talk about it. Okay?
Okay, thank you, sir.
You will. Any other questions, please? Any other questions? Okay, next class meeting we will do a lab. We'll do it for lab. And because this is the first time we do lab, so we may take the whole session for the lab. But later, if we have a lab, we may take a portion of the class meeting for lecture, and then we complete the lab. We will use Multisim, and I posted how we use it, and also user guide for Multisim. But we'll go through this together in the lab. So don't worry if something not clear now for Multisim. We'll do it together in the lab. Okay. But please be prepared for using the Multisim. Multisim should be offered by the school. So just please be prepared for this. Any questions? Okay, if you don't have questions, so thank you guys and have a good day. Take care.
Thank you, Professor.
Thank you,
Thank you,
Professor.
Have a
Professor.
good day.
You too, bye.
Thank you, Professor.
Thank you.
Thank you.
Yeah.
Have a good one.
You too, bye.
Have a nice
Uh,
evening, Professor. Thank
Oh,
you.
Professor, do we not have any assignments due for this week?
The lab next week. The lab next class.
Oh, okay. We're just doing it next class, but it's not assigned yet.
Yeah.
Okay.
Again, please review the examples we did. I told you before. We rely on the examples like more homeworks, but through the examples, okay? We did. Do it again, please.
Okay.
Professor, one quick question.
Sure.
And sorry for asking right now because I don't want to hold everyone else in the class. So in the previous lectures, we talked about the circuit for the transistor as well as the circuit for NOT gate.
Yeah.
I'm still a little confused about that. I was thinking, is this something I have to know for the class, or was it some like additional material you just
Oh
threw
no,
in?
this is just additional, just because some people they try to see what is actually happening inside this symbol. They just a symbol for the inverter or the NOT gate. But what actually happens if we put logic high or bit 1 as the input, we get bit 0 as the out, or 0, we get 1. So some people before asking about what actually happens inside. So this just simplified explanation for how if we put 1, how we get 0, if we put 0, how we get 1. So they just extra thing, is not. But of course, we must know the function of the NOT gate or the inverter. Like if we apply bit 1 as the input, we get bit 0 as the out.
Yes. And as well as I know the phases for the transistor, the saturation phase, active phase, cutoff phase, and the access amplifier and or switch. Thank you.
Okay.
Yeah, thank you, sir. I enjoyed the class. Have a nice day.
You too. Take care. Bye. Any other questions before we leave? You too. Take care. Take care. Bye.